All right, everyone, thank you for joining us. We are going to get started talking about the latest HelioScope and HOMER Pro integration and how you can use that in your workflow and to help your project designing. And I am Steffi Clowder from HOMER Energy. I'm the product manager. And I'm going to have Paul Grana, the co-founder of Folsom Labs, also join me. And we're going to each do a little design session and then combine them and see how the power of HOMER and HelioScope can be combined. And before we get too far in, I want you to know that there's a way for you to ask questions throughout the webinar. Look for the control window and just type your questions in there. I've got DeWalker on HOMER Energy side and Knut from HelioScope, and they'll be able to write you back, or we'll have a question and answer session at the end. And that's how that looks. And before we jump into a demo, I want to give a quick explanation about HOMER Energy. HOMER Energy is best known for its software products, and our software has been used by 175,000 people. We got our start at NREL, the National Renewable Energy Laboratories here in Colorado, and HOMER Pro is the flagship product, and it's used in several different markets. One is the behind the meter and energy bill reduction market, so that you can evaluate what new distributed technologies can help you lower your energy bill. And also very common is to use HOMER Pro in projects where you need to have reliable power, so grid connected resiliency, where high outages can have a very high cost on your facility. And this would be data centers or data centers or research facilities or manufacturing, and this includes weather disasters, Hurricane Sandy type examples. As well, we try to serve the markets of energy access and village power, which is bringing electricity to people that don't currently have power, and there it's especially relevant to choose between extending the grid or between creating a microgrid to serve your electrical needs. And finally, we have our island utilities, which is the perfect example of a microgrid, and that's also a cornerstone of HOMER Pro's business. So HOMER Pro, as I mentioned, is the main product we have, and it allows you to get insights into the complexities and trade-offs of these cost-effective and yet reliable microgrids and hybrid energy systems. And we're focused in that on accurate and unbiased and technology agnostic results. Just an overview of how HOMER Pro is set up and designed. You as the user are going to provide information on what technologies you'd like to consider. And that means we have a bunch of different technologies possible. You could do PV or storage or wind or hydro or generators, and the list goes on. And then you need to specify the amount of electricity that you want and when you want it. In other words, your load profile. And there's some necessary inputs like the economics of your system and the costs of those technologies. And you can download your weather resources through HOMER Pro. And given all this information that you can provide and customize within the program, HOMER Pro goes through many different simulations, and it ranks each simulation on the net present cost. And you can run risk analyses or sensitivity analyses on different variables and see what the impact of these variables on your results are. And hundreds of thousands of simulations are calculated, and these are ranked and optimized, and that will help you understand the different sizing options that you have and what impact your sensitivity variables have on your results. And what you get out of this is some useful IRR or economic metrics, and your performance metrics. You can have cash flow estimates, and there's multiple exporting and reporting features, and it allows for complete customization throughout the process. Now, of course, the focus of today's webinar and what we're very excited about is that HOMER Pro and HelioScope are very, very different tools, but they're both useful to the same group of people. And what HelioScope is great at doing is visualizing your site and evaluating the shading constraints and allowing you to quickly design your roof or ground mount system and include your inverters of choice. And HOMER Pro can do some PV modeling as well, but HOMER Pro really, its strengths are the economic focus on the hybrid technologies and how these technologies can serve your load for the best price. And HOMER Pro is an economic optimization as opposed to a spatial optimization. So HOMER Pro cares more about the economics than the site's shading or space constraints. And here's an overview of what we're going to see today conceptually. There's many different ways that you can use the integration between HelioScope and HOMER Pro, but in this demonstration, Paul's going to go through and design a HelioScope system within HelioScope, and with those power output results, I'm going to bring those into HOMER Pro's design process where you define your electrical needs and you choose your technologies you're considering and you input your costs, and from that, together the tools can create an economically optimized system design. And with that, I will turn it over to Paul and let him introduce himself and let him show you what HelioScope can do.
Great, thanks, Steffi. Let me get my screen shared here. Okay, Steffi, can you verify that you can see my screen? Okay, cool. So thanks everyone for joining the webinar here. And again, just a quick overview of the integration. Keep in mind that essentially when you're using the combination of HelioScope and HOMER, what you've got is two programs side by side. So the first thing that I should mention is you're going to have two logins, you're going to have two licenses, and the value of that is you've got two different engineering teams in terms of our engineering team and the HOMER Pro engineering team working on both products. So it's not that one is embedded in the other, it's that you can use both programs in how they're best built for, and then automatically export the output from HelioScope over to HOMER Pro for the microgrid optimization. So I'm going to do a quick run through and highlight a few of the important things for the integration. So first of all, we've got an example project here. Let me actually open up this this project. We actually chose a university in Mexico as an example of where you might typically be doing some work. So within a particular project, you would create a design. Now notice this is using Google Maps. So we actually have a few different mapping options, Google and Bing. In this case, Google's higher resolution, so I'm going to go with that. But just to mention here, HelioScope is a global product, as of course is HOMER. So now the images are going to vary based on where you are in the world. Now that, by the way, that's not just outside the US. You know, even within the US, there are areas that have, you know, great resolution and areas that have quite poor resolution. There are lots of areas in the US that look a lot worse than this. You know, so it's not a country-specific thing. One thing to note is that you can upload your own imagery. So if it makes sense, you might find a better image. You might have a drone. You might be able to purchase premium imagery, and you can upload that as an overlay as well. But just in general, you would define the physical area where the array is going to go. Notice I can rotate the view here in 3D. I might give this building a height of 20 feet. I might define a 4-foot setback around the perimeter, and then I'm going to set the row spacing actually based on the shading that these modules are going to see from 10 to 2 on the winter solstice. By the way, I'm doing a very abbreviated demo just to kind of show the principles here. You know, we actually have a more complete demo later today. If people want to join that, just chat with us and we can give you a more complete demo. But again, just kind of show generally how these would work together. Then I would hide the modules. Notice we've got this actually this inset that's raised a bit. So I'm actually going to define that as a second area of the roof. Give that a height of 10 feet on top of our lower roof. And then I'm actually going to do some shading analysis. So let's actually look at how often this little raised area is actually shading the modules around it. And then I can, you know, set the appropriate cutoff. So if I want to use a 15% shade threshold, then I would be removing about 71 modules. You can see that it's pulling off the worst shaded modules. Remove those modules, and now we've got our shade optimized array. So that's just kind of just a quick summary of the principles of the system. Now, another thing to note, which will become more clear later on, is we do have the ability also to set a max size. So now that's on a field segment basis. But let's say that we know that we actually want just a you know, a particular system size, maybe 131 kilowatts. So in this case, I would actually take this second field segment, open up the max size tool, and I might say max size of 20 kilowatts. And notice that HelioScope then stops filling in the shape once it reaches that maximum system size. Again, I mentioned that specifically because if you've been doing some work on the HOMER side and you know how much energy you're going to need from the solar array, then that's the way to target a very specific system size. So basically you would start from, you might start from the HOMER side, know how much solar you want, either in terms of energy or power. You could run a quick simulation in HelioScope to get the map between power and energy, and then use this max size to set that power. So I just want to flag that as something that's a little bit doubly important with the HOMER integration. And then finally, when it comes to electrical, I could just choose any string inverter, and then HelioScope basically does the electrical design automatically. It sizes the number of inverters I would need, given that we've got 130 kilowatts DC. I might need 112 kilowatts AC, given that I've got a 22 kilowatt inverter. And it sets the string size based on the nearest ASHRAE location. Looks like there's a I think that's an airport, and that tells me the high and low temperatures on record combined with the module voltages and the inverter voltages. So basically with that, we're done with a design here. So it's a pretty quick path to go through. Another thing to mention, again, for those that are outside the US, we also, of course, support metric for both the distances and the conductors. So if you notice, what I just showed was in feet, and if of course if that's what you use, then that's wonderful. But if you're using metric, it's very easy to do. Click on your name, go to preferences, and you can update that there as well. So that gives us enough to have an actual design completed. Notice there's a few things that we get from that design. First of all, a bill of materials. So we've got 400 modules, 415 to be exact, just under 3,000 feet of number 10 copper wire. Again, both of those are you know, American conventions, but you could switch to metric for both. We also have an image of the array here. Notice you can have your own custom logo on the image. You can customize the details that you want to see on that image. And then we even have a CAD file. So actually I can export this to a CAD file, and then I'll be able to open this up inside a CAD program. So that's quite powerful. And then finally, we even have a single line diagram tool. So if I go under the electrical design, if I click on the SLD tool up here, it actually shows me that in this case, I've got 5 inverters that are all going to have 3 strings of 15 and 2 strings of 19, and that's the best way to get exactly 415 modules accounted for, given the series of constraints that we've got for this array. So that's kind of the quick summary. And then finally, if we go to the simulation, on the reports tab here is where we simulate the array. Now, speaking on the simulation, this is where it particularly becomes important for the HOMER integration, because this is what's exported to the HOMER side. So one thing to point out is when we're simulating the array, we are simulating every module, and we're simulating the detailed physics. So keep in mind, our module model is actually 4 equations. This is the overall high-level equation. We also calculate the photosaturation current. Here we go. So here's the overall diode equation, and then there's actually 3 other equations for photocurrent, reverse saturation, and shunt resistance. So that's the physics that's applied. every single module, every single hour. So for example, this simulation that we just did has just over 400 modules being run against about 4,000 operating hours. So that's roughly 1.6 million separate calculations of each module's IV curve every hour of the year. So if I open up this report, we've got all the high-level metrics at the top: system size, DC and AC, the energy calculations here, the total energy production, and then the two key ratios, performance ratio and specific yield ratio. We show you the monthly values here, and I'm going to come back to that because behind these monthly values are hourly calculations. This is the table that matches up to PV-Syst. So for those that know of PV-Syst or use PV-Syst, keep in mind that HelioScope's math is the exact same math as PV-Syst. So if you run two models side by side with all the same inputs, you're going to have the same outputs. You can line these tables up to within a 1% tolerance. Then the bill of materials, and then that design image that we showed at the bottom. So again, as you can see, you get a lot of things for just a little bit of input. So both the physical array, so bill of materials, image, and CAD file, electrical details around the single line diagram. There's a shader report that I'm going to download that as well here. And then finally, we have the energy numbers. Now, speaking on the energy numbers side, or sorry, let me just go back and pull up the energy numbers while that shader report is downloading. So on the energy number side, the final thing just to show, because this is quite literally what is exported to Homer, is this CSV file here. So notice if I click the CSV button, this is going to download essentially an Excel file here. So if you ever want to look at that yourself, you can. Notice every completed simulation has a CSV button here at the very top. If I go to this, and then I can open up this CSV file here. Sorry, just give me a minute to get Excel loaded up. So this has a few properties. First of all, it's got 8,760 rows, one per hour of the year. Then the first 8 columns or so are the weather file. So the date and time, the sunlight, temperature, and wind speed. Then we're calculating the sun angles. We're calculating the irradiance, so things like GHI, diffuse, direct, shading, shading effects, reflection effects, soiling losses. All that gets us to the end of the irradiance, and then the effects inside the array: module temperature, module low light performance, mismatch losses, wire losses, inverter losses, and AC losses. And then the final thing is grid power here. So this column is typically the most important number because this is what you're actually getting. How much energy are we getting every hour for every hour of the year? So again, that's what HelioScope is generating every time you run a simulation. And then that's the primary thing that's exported to Homer. But just wanted to point out that behind those numbers, A, you can always download them yourself if you want, and B, you can, and B, behind that is a detailed weather file and module level calculations for the array. So that's basically the overall thing. The only other final thing that I wanted to point out that's going to become relevant in just a moment is the fact that if you see right here, so when I click on one of these simulation reports, notice at the very top you see this number which is at the moment 1544265. That's the simulation ID. Keep a note that's the actual simulation ID. Also notice, by the way, that number is, you see it right here on the Excel file, 1544265. If I download a PDF, you'll see that simulation ID on the PDF. So the reason I'm pointing that out is that ID, again, you see this PDF right in the file name of that PDF, 1544265. That's going to be the simulation ID that you're going to keep an eye on when we get over to the Homer side. So we've had a few good questions come in. I'm gonna, though, I think we want to save the questions till the end. So at this point, I'm going to pause and kick it back to Steffi. Oh, sorry, one more thing. I just realized that from a sharing point of view, I wasn't sharing my overall screen. So let me just quickly pull up the Excel file just to show.
Yeah.
Oh, actually, that's fine too. Yep. Sorry, go for it, Steffi.
Sorry, thanks, Paul. That was great. Right, so in case you're not yet familiar with the Homer interface, we'll take it slow and we'll show you how you can bring in that production data that Paul was talking about into Homer Pro and continue modeling. And where we are right now in the Homer Pro interface, this is the home screen. And so here is where you can type in the name of the project and my name. So I'm Steffi, and we're going to do this university. Here's our location search. We're going to do Monterey. And the primary function or the use of defining your location is so that you can download the resources. And of course, if you have your own solar data, you can upload that, but this is how you get to it in the built-in HOMER Pro way. So now we have our solar data defined. And before we leave this home page, I'd like to point out that there's some high-level economic information here in the corner, like the discount rate and the inflation rate and the project lifetime in years. And because HOMER is an economic model, all of those are going to have an impact on the results. It matters how much money is worth in the future, essentially. And these little icons here, these are for the sensitivity analyses. So since these are important variables, you can always define a couple of these variables and see what the impact is on your results. But we'll come back to that later. So the first thing you do after defining your location and your solar resources is define the electric needs that you have. And so similarly, if you have information from on-site, that is best to upload. And good information on your load is critical to the design process. But today, we have three different options. We can upload and import the different information that you have, or you can use a synthetic profile, which HOMER has been using for many, many years, or new this year, or 2017, was our accessing the OpenAI database. And unfortunately, it's only available for US locations right now, but we can scale this to our Mexican university. We're going to choose a secondary school in Texas. Okay. And my computer's a little bit slow today, but it'll pop up with the information that we've just inputted. And then we can further customize it to our needs, or to the information that we have at hand. All right, there we go. So this is our daily load profile, our seasonal load profile, and a DMAP or a heat map, which is a great way to visualize the whole year. And you can see these vertical stripes are the weekends, and the summers have, to be expected, a higher electrical demand. And say that you know you can scale this load profile to a value that you might have. So let's make this school 7 megawatt hours per day, and you can add some sensitivity. You can analyze your risk there if your load is more than expected or less than expected. Once we've defined our load, we'll call it our university. You can see that it added to the schematic, and you can always use the schematic as kind of a navigation tool to go back to and re-edit the possible technologies that you're considering. And the first technology that we'll consider, of course, will be RPV. And HOMER Pro, as we said, has some capabilities around PV, but if you prefer using HelioScope, we want to integrate that into your workflow. So here's what the HOMER-esque PV would show, and you can do a dedicated converter, an inverter in that case. You can consider temperatures, and you can consider various forms of tracking. But today we really want to focus on our HelioScope integration. So we've made this HelioScope wizard here, and that allows for 2 different ways to incorporate HelioScope. So This introduction explains that to use the API method, you need to have an active HelioScope account. And that is the version or the method we're going to use today. If you didn't have an active HelioScope, you could, from your colleague or from the time when you did have an active HelioScope, you could have had that CSV file downloaded, as Paul was talking about, and then you can upload that directly from your computer. And that's the other way that you can get your HelioScope information into HOMER Pro. Here's where you log in with your credentials. And those will be your HelioScope credentials, to be clear. So these are your different projects. And Paul was kind enough to share his university project with me. So here's multiple simulations with that under the same project. And you can click through and see which one you actually mean to design. So here you can see design number 1 with 135 kilowatts. You can look at the DMAP here to show when it's producing and get a concept for the total energy produced by the array. And if that looks good, you can click next. And this is a screen to remind you that you're still going to need to input your data for the whole, your cost data for the whole system once you're done with this screen. So here we are, HelioScope was added to the AC bus, and now we need to define the costs of our whole system. So for the 135 kilowatt system, we can enter, let's say, $2 per watt. That would be 270,000, and say a $10 per kilowatt per year O&M would be 135, and the life of their system will be about 25 years, say, which is equal to our project life. So then replacement costs don't really matter. And here's where we're choosing in our search space either to include the HelioScope production data with the 1 or to not include it with the 0. And you can use the optimizer, but we'll come back to that a little bit later. Right now, we'll define our other components, like say the university is connected to the grid, to be expected. And HOMER's way of modeling the grid is multifold. You can do a simple rate here, which just defines the power price and the sellback price, or you can upload real-time rates if you have that information, or you can define a time of use rate structure where between certain hours you'll have a different rate than, so option HOMER includes is the grid extension. If you are considering any kind of grid-related costs where you're balancing, should you connect to the grid or should you be off-grid? That's very, very useful there. But today we'll keep it simple, keep it quick. We'll go for the simple rates. And let's see, as a price, we'll guess 13 cents. And since we don't want to really incentivize selling back to the grid, we'll just give that 1 cent. 1 cent per kilowatt hour. And now we have a system with the grid, your load, your PV. And the last thing we might want to include is storage. And HOMER Pro is really an excellent tool to consider storage. And we have several models. Our advanced storage module here with the ASM tag on it, that includes temperature degradation and cycling degradation. And it is really a truly complex and useful tool to visualize the battery over its entire life. So again, we'll need to define our cost, and this time it's per battery or per kilowatt hour in this generic case. Because we're defining our battery separate from the battery's converter and power electronics, we'll make that a little bit cheaper, more reasonable. And this time we'll use the HOMER optimizer, which will just essentially find the number of batteries that is ideal for this load. And now it's giving me a warning here. These are my required changes before I can calculate. It wants me to add a system converter, and that's what we'll do. So for $300, that'll be our power electronics and converter with regards to the battery to connect the DC bus to the AC bus. And those prices will be, we'll leave those as they are. We could use the HOMER optimizer, or if we knew that, for example, our converter only comes in 8 or 16 or 24 or 32 sizes, we could use that as a way to more correctly size our system. And now we have no more required changes. We're ready to calculate, so we can do that. Just because my computer is running a bit slow today, I'll go straight into the results. So this is from what we had designed here, the results that we get. We didn't consider any kind of sensitivities or risk variables. And what's optimal, according to, this is sorted on the net present cost, is this PV plus grid system. If you, obviously, the cost of energy is very close between all of the different system architectures. So depending on your view and what variable is most interesting to you, you can sort them on different things, just click the box, but right now it's sorted on the net present cost. And another very useful thing is comparing the economics at a high level between what your payback times and IRRs would be, and we're going to compare it in this case to the grid-only system. So here you can see that the PV system has a 7% IRR, and the PV plus storage system has the 6.5% IRR. So very similar, and you could, as a developer, probably make the case for either with just a small difference in the initial capital required and a lower operating cost than just buying your electricity from the grid. And that's where HOMER really thrives, is showing you the trade-offs between your CAPEX and your OPEX, basically. And to get a closer deep dive into one of the systems, you can always double click on it. So we'll consider the fully hybrid system with the storage and the PV. And these are the simulation results where you can see the cost summary, where we are. You can look at it in terms of annualized costs and costs by component type, as well as high-level information on the cash flow. Discounted here, I always find it interesting. That's where you can see how important it is to correctly, or to play around with your discount rate and your inflation rate, because that'll have an impact on what that curve looks like. And these results can be exported as well. We have a report that will help you if you want to use any of this information in your proposal process. The compare economics, we saw a high level before, and here's a couple more metrics on comparing our fully hybrid system to the base case. Our electrical tab shows us high-level information on what's happening with the grid purchases and how much HelioScope is producing, and if there's excess electricity. In this case, the renewable fraction over the whole year, HelioScope system is serving 7% of the energy in total, but there is some time when there's a certain day or days when it's serving all of the load, actually, and we can see more information about that there. Or up here is where you can see energy purchased from the grid versus energy sold to the grid. And you can get more information on the battery's performance and what the converter is doing to work with the battery and the emissions here. But I'm curious about these sellback days. So if you want to dive in to the HOMER results, you can see this plot here, which is the time series over the whole year. And what it's showing here is the AC primary load. But after we install our PV, the PV is serving this much now. And we saw that in springtime, there were certain times where we were selling back to the grid. So that's where the PV power output is above that, the weekend need. So it seems like we've sized our system close to the weekend's average load over the year. And what I'd like to see and explore more is if that is the best thing that we can do, if the sizing that we designed within HelioScope is the best that it can be, or if there's maybe a slightly different sizing which would be more economic and more beneficial. So we're going to go back just quickly to the design view. And we're going to go back to our HelioScope. Instead of saying the search space is either with your system or without your system, we're going to say it's either 0% of the system you designed or 100% of the system you designed. Or if you had the capacity to, or the space to consider more PV than what you design in HelioScope, then you could go up to 200% of what you designed, say. And then HOMER Pro, the optimizer, will find that sweet spot in there, which is the best sizing from an economic standpoint. So we could calculate now, or we could think about what are our high risk factors for our project. What threats does this project have? And grid price is always something to consider. So what would happen if 13 cents seems a little high, maybe 7 cents would be better? Or what would happen with a 15-cent energy price? And given this, it'll rerun the model with each of those parameters, and you can see how those parameters affect the results, which we'll see in just a minute. And likewise, what would happen if we didn't use a $2 price per watt, but instead a $2.5 price per watt or a $3 price per watt? So what if the capital expenditures increase by 25% or by 50%? And with these inputs now, we have to rerun so that we can get our new results. With these inputs, we'll be able to see what the impact of a higher PV price is, or what the impact of the lower grid price is. And sensitivity variables do compound the calculation that's being run. So just to move quickly, we have some prepared results of that system that I just ran. So here are the various power prices that we were considering, and here are the various PV prices that we were considering. So the $2 per watt is the one, and 25% greater than $2 per watt is the $2.5 per watt, and $3 per watt is down here. So as you can see, once you're up to $3 per watt, it makes the case for PV really difficult. So the above table are the sensitivity cases. And if you click into a sensitivity case, it'll change the results down here. And what's showing above is just that top, the winning system, essentially. So under the case of our $2 per watt PV installation and 13 cents power price, the winning system is just PV and the grid. But if we increase or if we lower the power price, then the winning system is just the grid only, and it beats out the PV. So in this way, you can make conclusions about where the trade-off point is, and at what price is this project worth it, and at what price is it not, and do your risk assessments in that way. And once we have two sensitivity plots, we also have the option to view this as more of a graphical, in a graphical way. So we'll click our graphical tab here. And the one I really like is the spider plot, so that you can see what are the impacts on net present cost, or say cost of energy, given the higher power price, given the lower power price, and given the variance in the PV installation price. So we have a couple different visualization tools here, which I'd encourage you to check out. The OST chart is appearing a little bit funny just because there's only data points on these little triangles, or on these diamonds here, and it's extrapolating between the two. But essentially, at higher PV prices, a grid-only system makes sense. At lower PV prices with higher power prices, the PV system in combination with the grid makes the most sense. So we'll switch back to the normal tabular view. And as you can see, we didn't talk about this yet, but given our case here, with the 13-cent power price and the $2 per watt PV installation price, here it's recommending that in this case with the PV system only, you should install all of the space that you had for your PV allotted. But if you're combining it with storage, maybe you'd want to consider a smaller PV. And that's actually, it's kind of a surprising result, actually. So let's see if that's common across the board. Yeah, so here's how you would size your HelioScope array based on the HOMER results. This is recommending that you consider a smaller PV array, actually, a PV array that's 77% of what you had planned. And so in that way, you can do iterative modeling and go back and forth between HOMER Pro and HelioScope in order to find the most economic and feasible system. The last thing I think I'll mention today is our reporting options. If you need to use any of these results in your proposal writing or in your presentation making, we have export functions here, which can export this table here or this table here. And we have the report writing function within the simulation results, where you can export the actual time series plot over the whole course of the year and what the dispatch is doing, all that stuff. And with that, you can make a more convincing presentation. So the last thing, I think, before we turn the floor over to question and answer system, let's see. You can download HOMER Pro right now for free. There's a 21-day trial. So I'd encourage you to check that out at homerenergy.com. And also, let's see, HelioScope, of course, offers also a 30-day free trial. And Paul can tell you more about that as well. And now I think we can open up the floor to any kind of questions that you may have that Walker and Knut didn't get a chance to answer. Okay, I'm sorry. Paul's going to take the questions on first, and then I'll take the questions on towards the end. So with that, I'll let Paul take the floor. Thank you, guys.
Thanks, everyone. I'm just going to, I'm actually going to share my screen briefly, so give me one more moment to get my screen up, and then I'll run through. We've got a few good questions coming in. All right, so, okay, perfect. So, a few things. Okay, everyone should be able to see my screen now. I'm going to quickly run through a few aspects of the questions that just came in. First of all, just in terms of overall access and how do things work. So first of all, at least from the HelioScope side, I'm pretty sure from the HOMER Pro side, there's no upgrade needed. So basically, if you've got access to HelioScope, both during the trial period and then during, any during a paid, paid license, that API tie-in is totally available. No other costs, no other upgrades. Also, note that HelioScope is cloud-based. There are a couple of questions about, if there's anything to download, how that works. Everything I've been doing has been in Chrome, and so as long as you've got access to a browser, we recommend Chrome and Firefox. You should be good to go. Speaking of Chrome, I apologize. I had earlier only shared Chrome, not Excel, so that's why earlier when I was demoing the Excel part and no one could see anything, human error, as it usually is the case. In this case, I'm human. So just a real quick run through of what that Excel file looks like. So again, this is from the output from a HelioScope report. This CSV button is going to download a file that looks like this. 8,760 rows, because that's how many hours are in a non-leap year. Weather data, so irradiance, temperature, and wind speed. Our calculations of sun angle based on your exact latitude, longitude. Our calculations of the sunlight effects, things like shading, soiling, reflection losses. Then we get into the physical solar array. So then it's things like temperature, module low light behavior, mismatch losses, DC losses, inverter losses. So there were a couple of questions about how things are calculated, particularly around wire losses and inverter losses. So please note that HelioScope is calculating both of those, both DC wiring losses, AC wire losses, assuming you've got the AC system defined, and inverter losses. So when you get the output here from HelioScope over to HOMER Pro, that's going to be net of basically all system losses. The other thing just to point out is you can see those losses here in this loss table. In fact, if this matches up, here's a small little trick. Notice if I select this column, Excel just shows me the sum of the column, 205, 887, and you can see that here it matches up. It's rounding, so it's actually 887627. It rounds to 888.0. But yeah, you can see that that those numbers do match up. So for example, in this case, I've got 4.3% mismatch because I've got actually 4% shading losses. But then I've also got, here's a little bit of clipping at the inverter. My DC losses are just 0.3% because I've got short DC runs. My inverter loss is 2.4%, and then my AC loss is 2% because that's what I've got it set to in my condition set. So again, there's a few different aspects of how those things are done, but just kind of illustrate the principles that yes, those factors are factored into HelioScope, and if you want to verify what they are, you can see that here in the HelioScope output reports. The other thing that again I showed earlier, but just didn't have a chance to show without sharing non-Chrome is here's the CAD file for this for the actual layout here with the modules in a fully editable CAD file. So again, just wanted to show that because I was talking about that earlier. Now, one of the other questions we had is, how does HelioScope work on a flush mount roof? Because I was using a flat roof earlier. So just a quick illustration of how things work on a flush mount roof. Notice that the principles are all very similar. You would draw a field segment. You define the modules within those field segments. The only difference is the racking. You would make flush mount. That means that the tilt and azimuth actually defines the angle of the surface itself. Another aspect that would often come into play is the alignment. So if you notice here, this is a strict grid. So it's basically a checkerboard. That's this third alignment option. If I choose the second one, it actually is going to try to squeeze in as much as possible. Notice these are staggered. The rows are staggered. So in this case, it's the difference between having 16 modules in a 5 kilowatt system or 19 modules in a 6 kilowatt system, just by having those modules staggered as much as possible within that shape. And then the other thing I would mention is when you're in flush mount mode, you can actually set the orientation of the field segment based on either the top or the bottom edge. So in this case, I select set to top. Let me actually tweak that a little bit. If I set that to top, then it's going to use the ridge to tell the software, which direction that roof surface is facing. Because in some cases, like this one, I might have not very good gutter lines, but I've got a better ridge line. So you've got two options there when you're in flush mount, because a lot of times the residential buildings, you either have a good ridge or a good gutter, but often not both. And then the final thing to point out is we actually have a new set of features. So for our existing customers, this is actually new. The ability to manually change or add modules. So just to show this very briefly, I've got my standard layout here in portrait, but I've got room for maybe a half a module worth of layout at the top. So I'm gonna go to this manual module control, and I can actually either add in one landscape module here. Oh, sorry, let me go back and sorry, just need to fix one thing about the alignment. Or if I want to add in a few, I could actually drag and lay out those additional few landscape modules. So in this case, I've got a mix of portrait and landscape. In fact, you could even select a single module and just move it around. In fact, if I wanted to hold shift, it'll snap it to be flush with the row beneath it. So a few features there. Again, I'm just kind of showing it very, very briefly how HelioScope works for a flush mount angled rooftop where it's not the exact same. One of the other good questions that came in is how is the HelioScope output going to compare versus the HOMER output? So probably the best way to talk about that is to talk about HelioScope versus PV watts, because I believe the HOMER PV simulation is more or less PV watts. So there are differences. HelioScope is it's based on a bit more physics. Now that sometimes means we get different results because of course we've got 42,000 modules, all with different physical properties, whereas PV watts and simulation tools like that don't have as much detail. So that could be a source of differences. But frankly, one of the biggest differences is just the weather file. So if you've got a similar weather file, very likely your results will be pretty similar. If you've got a different weather file, then your results will be different. Similarly, again, the module properties, HelioScope has properties of every single module and how those are going to change at different irradiances and temperatures, whereas PV watts has more standardized things like temperature coefficients, etc. And then this table shows how you can line up those losses. And then finally, this table goes through step by step of what's included in one or not included in the other. So you can see that, for example, output at irradiance is the low light behavior. So the actual semiconductor properties where modules don't like low light as much as they like full sun. HelioScope does that natively, PV watts doesn't. On the other hand, what else do we, PV watts has a loss factor for just the connectors, whereas HelioScope doesn't include connectors. We include conductor losses, but not the connector losses. So we can of course share this if you just ask us. One thing to note is, though, let me see if I'm offline. There's a live chat here, so it's a little bit large here, but we do have live chat support. So if you have questions, ideas, if you just want to, if you just need a friend, we've got live people there, so don't hesitate that. And so if you just ask for this, we can send this link to you guys in that chat window. That's kind of why we do those. Oh, wrong thing on my clipboard. So I think that was most of the questions here. I'm just going to check for the last couple things. Let's see. Oh, and then in terms of how system sizing is set in HelioScope, so keep in mind that if you apply the max size, then it'll use that max size. If you don't, then HelioScope will just fill in those field segments. So in terms of the principles of how it works, it'll be based on the actual field segment area. Oh, and then the last thing, I was downloading this before, but I just didn't want to wait for it. But notice that this is what the shade reports look like. So a couple things here. One, this shows the heat map of how much shading each of these modules is getting. In this step, it actually shows this offset for the penalty for not being the optimal tilt and orientation. Notice it actually shows you your ideal tilt and orientation at this exact location based on the weather file and sun angles. And then of course, the shading losses, which is the solar access, and the TSRF is the composite there. This actually shows a 45-degree perspective of that system as well at the bottom of that shade report. So these shade reports are actually used in the US. They're used by a bunch of states and incentive programs as a replacement for a sun eye, so that you could actually have a third-party verification of your shading analysis without having to go to the roof, but they're also just kind of nice things to have in there. And again, that's available in any simulation that you run in HelioScope. So I think that's pretty much it. One other question was on P50 versus P90. So yeah, HelioScope doesn't have P90 files by default. You can purchase P90 weather data, but in general, the weather data that we've got is going to be typically P50. So just to show very briefly where you can customize that. Oh, sorry, I might have some connectivity issues here. Let me try refreshing my page. I might be offline. So anyway, That's how you know it's a live demo, is when you have internet trouble. But yeah, otherwise, let me see if it's any better here. But yeah, otherwise, you can customize the weather file, but by and large, the weather files that we've got are P50 format weather files. So with that, I'm going to send it back to Steffi for any Q&A for the homework.
All right, thank you very much. And it does look like we're a little bit close to the top of the hour, so we'll try and make this a little bit shorter. But some interesting questions did come up throughout the hour. First of all, Paul mentioned this, but I want to reiterate that these features are available now, and that there's not different subscriptions necessary so that you can get this integration. These are for our users and for our shared users especially. Another thing that came up, good question, whether HOMER Pro can work within Windows. Or in Windows it works. It's not a program designed for the Mac, so with the Mac you'll have to use Parallels. It's designed for the PC. And we have a user questioning where they could get typical values to enter into HOMER Pro. And we do try and make it as easy as possible. So we have default values that you can always use, and we have various forms of help. We have a help manual that's both online and built into the software. And we have our knowledge base, and we have a support team here that can help you. But essentially, you can use the default values that are already in HOMER, and we give generic components with pricing, and so that's a good starting place for a new user. Another interesting question we had was talking about we use the simple grid rate in this scenario, and the question was asking whether there was a way to define both demand and energy charges. And yes, there is. I can show you that quickly here. So within the grid, I talked about simple rates, real-time rates, and scheduled rates. And here's where you define various different time of use rates for your energy charge. And similarly, you can define various different times where a different demand charge would apply. So that's a great question, but HOMER Pro can take on that complexity. And in fact, we are building out our capabilities in this area to better serve our behind-the-meter hybrid energy projects. And we're going to make an exciting announcement towards the end of the month, and hopefully with a release in mid-March for HOMER Grid, which will be a product separate from HOMER Pro that will help you especially identify opportunities to reduce your demand charges. But HOMER Pro is our flagship product, so you can get so far within HOMER Pro, and it's so customizable that you should definitely start there with our free trial. And another question we had, which is really good, was about how we're comparing the economics from the generators versus the economics from storage or solar. And the answer is those are the economics, the costs that you should put in and make as accurate as possible. And comparing high initial investment costs to high operating costs in the future, that's what this tool is good for. So HOMER Pro is a great tool to compare generators to solar PV and to see what makes sense in the long term, if a high investment can pay off and be better than a generator which would continue to have operating charges over the course of its lifetime. So that investigation is exactly what HOMER Pro is good at. And last, we had a couple of people asking about whether the webinar was going to be shared. And yes, it will be. In about a week, it'll be up and emailed. So thank you everyone for your time, and I hope that you can see the power between this integration of HOMER Pro and HelioScope and modeling in a truly integrative and iterative style to help your workflow and to help your your business cycle. So thank you very much for your time. And with that, we'll go off. Bye.